Lesson 3 of the Geometry Probability Unit, Probability with Two-Way Frequency Tables. This lesson will teach me to use a two-way frequency table to determine the probability of events and define conditional probability. The definition of conditional probability is that the probability an event has occurred given that another event has occurred. So the example I used in class was, for instance, find the probability of a student passing a test given that the student has studied. The idea of conditional probability is that this has already occurred. This slash mark right here is read as given. So the probability that a student will pass a test given that they studied. So if you were to think about your class and maybe there are 25 students in the class, I'm not asking for the probability of a student passing out of 25 or studied out of 25. I'm asking the probability that a student will pass the test given that they studied. So no longer are we using the entire 25 students, we're using how many people studied. The formula, if you will, this says the probability that event A will happen given, this line again means given, that event B has already happened is, so this says P, probability, A given B equals the probability of A and B all over the probability of B. Notice the B here at the end and the B here on the bottom. There's a relationship here just as there is here, but what this does is it limits the sample space. So again, you're no longer looking at the total number of people in your class, but that denominator now is maybe the 15 people who studied out of the 10 who passed. So you're limiting that sample space. Down here in this second yellow box, it's saying the exact same thing, just the other way around. The probability that event B will happen given event A has already happened is the probability of A and B over the probability of A. So however you are limiting that sample space is going on the bottom. A two-way frequency table is a visual representation of the possible relationship between two sets of data. So the two sets of data we're asking here are either sports car or SUV, and the other being gender. So this 21 represents 21 males who drive an SUV. This 135 is the number of females who drive an SUV. There are 39 males that drive a sports car, 45 females that drive a sports car. And then we have totals. There are 60 total males who were asked these questions, 180 females who were asked. There are 156 SUV drivers. There are 84 sports car drivers, and a total of 240 people were asked to be a part of this survey. So the two-way frequency table is breaking up all of your different combinations of how people responded. The two-way frequency table is going to make you finding the probability a little bit easier because all of the numbers are already given. So for instance, the probability that somebody, well, let me back up. It says use the two-way frequency table to find the following probabilities. So picture a survey of 150 people with two questions asked. Did you eat or skip breakfast versus what kind of mood are you in? So of the 150 people who were asked these questions, how many of them ate breakfast? We go to the ate breakfast column, and 90 total people out of 150 ate breakfast. Another question. We wanted to ask those 150 people, what's the probability of them being in a bad mood out of the 150? Well, how many were in a bad mood? Total, there were 50. Next step. Letter C asks for the probability that somebody is in a good mood and that that person skipped breakfast. Good mood, skipped breakfast is 22 out of the total number of 150. The probability that somebody skipped breakfast and was in a bad mood is the 38 over the total 150. Now these ones, next three, are these newer varieties, where the idea here is that this slash is the word given. So it says the probability that somebody ate breakfast given they were in a good mood. So the number down here isn't going to be 150. It's going to be the number of people who were in a good mood. So find, let me erase all these other markings, and let's look at just those people who were in a good mood. The good mood row is right here. So there were 100 people who were in a good mood. What we also need to find is on the top of this, we need to find the probability that somebody ate breakfast and was in a good mood. So how many people ate breakfast and were in a good mood? 78 of the 100. So in this next one, a lot of students see that probability of eating breakfast given good mood versus probability of good mood and eating breakfast, and they think that we're just switching these fractions. But instead what's happening is that this ate breakfast is limiting our sample space. I'm no longer looking at all 150 people, but instead when we go to answer this question, we're looking at only the number of people who ate breakfast. So think about circling that. If all I was to do was to look at only the 90 people who ate breakfast, how many of those 90 people were in a good mood and ate breakfast? Well, of those 90, the good mood who ate breakfast was that number right there that I just covered up, 78, which is the same one we had over here because we found where good mood and eat breakfast, good mood and ate breakfast. The difference was what you were limiting it to. So for problem G, it says the probability that somebody is in a bad mood given that they skipped breakfast. So we need to find first the probability that somebody skipped breakfast. That's how many people you'll have the probability out of. And on the top, it's the probability of somebody being in a bad mood and skipping breakfast. Sorry, it's getting hard to write. All right, so again, think about circling the only thing that you're looking for. We're trying to find the number of people who skipped breakfast. So where's that column? It's right here. And of those people who skipped breakfast, how many of them also were in a bad mood? So 60 skipped breakfast and 38 of those people were in a bad mood. So 38 out of 60. Take a second, pause the video, and try the next part on your own. Go ahead and check your answers. The probability of finding somebody who can fly is 38 out of 100. The probability of picking a male is going to be 48 out of 100. The probability of picking somebody who has wants another superpower and is female is 8 out of the total 100. As I was teaching this, what I found is that students were confusing this and symbol with the given symbol. The only time we're limiting the sample space or changing that denominator is with the idea of given. This just means and. So there are 8 people who were female and wanted other superpowers out of the whole 100. People who wanted invisibility and were male were 12 out of the 100. So when we get down to the conditional probability, these are the newer concepts. These are asking for the probability of male given that somebody wants to be able to fly. So look at how many want to fly. It's this whole row. How many of those 38 were male? 26. So 26 out of 38. If we look at the next one, this one says, I want to know the probability of people who want to fly given that you've already chosen the males. So this time, look at all the males. How many of the males also want to fly? Well, 26 out of the 48. And then letter G, find one more color here. The probability of picking somebody who is choosing invisibility given that all the females have already been selected. So look only at the female column, all 52 of them. How many of those females would like invisibility? It's 32 out of 52. So when we look at conditional probability, I do think that it's easier. Most probabilities are easier with that two-way frequency table because all of the data is already given to you and organized. It's a little bit harder otherwise. So what I've given to you here is what's called a sample space. A sample space is all the possible outcomes. So this says two six-sided dice are rolled. Find the conditional probabilities below. And I'm not going to make any mention of any of this stuff right here. Whoops, I can do it. Whatever. So finding the conditional probabilities below. If you roll one dice, you're looking at this red one, your options are 1, 2, 3, 4, 5, 6. If you roll the black die, your answers are, or your options are 1, 2, 3, 4, 5, 6. So you can roll a 1 on the first and a 1 on the second, a 1 on the first and a 2 on the second, a 1 on the first and a 3 on a second, and so on and so forth. So what this particular problem is asking is it says the probability of rolling a 5 on the second die given that you've already rolled a 4 on the first die. Well, how many different times can you roll a 4 on the first? This one, this one, this one, this one, this one, and this one. So there are a total of 6 ways that you can roll a 4 on the first dice. Now what I want to know is the probability of rolling a 5 on the second and that 4 on the first. So if we look at these options, a 5 on the second and a 4 on the first, there's now 1 out of all of these combinations. So that sample space has been limited down from the original 36 options. It's been limited based on 4 on the first die. All right, letter B. This is asking us to find the probability that you roll doubles given that the sum of the dice is greater than or equal to 8. So in the denominator, we're finding the probability where the sum of the dice is greater than or equal to 8. Those are going to be these options right here. All of these options add up to 8, and all of these options add up to more than 8. So we're no longer talking about just the probability of rolling doubles. We're talking about the probability of rolling doubles given that you've already rolled one of these 15 options. So how many doubles are there within here? The 4 over 4, the 5 out of 5, or 5 and 5, and the 6 and 6. So there are 3 possible ways to roll doubles. Oops. To roll doubles and have a sum of greater than or equal to 8 over the total number. And lastly, again, we're not reversing this fraction, but you're limiting the sample space in a different way. This time, look at your whole sample space of all these 36 options. You want to find the probability that you'll roll a sum that is greater than or equal to 8, but this time, you're limiting the sample space, though, to the probability that you'll have first rolled a double. So how many options of doubles do you have? 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So given that one of these these have already occurred, there are 6 total options. What's the chance that of these doubles, you'll get a sum of greater than or equal to 8? The 4 and 4, the 5 and 5, and the 6 and 6. So there are 3 options where the sum is greater than or equal to 8 and it's a double out of, think about all the doubles. So 3 over 6 or 1/2. Do the best you can. Please let me know what questions you have. Thank you so much.